So here are the tools that I use and recommend. We're going to spend probably the most time with Moscow State University, spend a little bit of time with SimWave. They are here at the show. They've got a live and a VOD evaluation tool, and if you're interested in this, I recommend you go talk to them. Tektronix, a little bit of a different focus here. We'll cover that in a moment, but Tektronix is here as well, and they've got an excellent video quality measurement tool that's tied into overall QoE and QoS. So they're not, the Moscow University tools compare one video to another. The SimWave tool and the Tektronix tools are more in the context of an overall operation. How do you ensure overall quality of experience? So they're a little bit of a different focus, a little bit of a different approach. So here's the VQMT workflow. VQMT is video quality measurement tool. And it's pretty simple. You load a source file here. You load either 1 or 2 compressed files. You choose your metric. You press start, and it computes the metric for you. And you get this results visualization screen. Now, what do you like about this screen? Well, it tells you a couple things. Number one, and we're going to look at these files a lot during the course of this presentation, but we've got the Zoolander clip, the first 2 minutes of Zoolander, encoded using constrained VBR, 200% constrained VBR, which is in red, and then we've got it encoded with one-pass CBR, which is in green. So what we see here is the scores are relatively consistent, but we have some regions where the video quality really drops significantly. So even though the scores in this case, this is a VMAF rating, I think the constant bit rate encoded file might be a 90, and the constrained 2-pass VBR might be a 91. So you would say, okay, no just noticeable difference. Why have a 2-pass encoding? Why double your encoding costs? You might want to consider doubling your encoding costs because there are regions in the video file that are going to look bad. They will, and then you've got to make the evaluation, will they affect QoE? So here's the entire comparison. This is the entire file. This is the zoomed in region from here. So this little green area is what you see down here. And you can slide through all the frames using the slider. You can use the arrow keys down here. And then if you want to view a specific frame, if you want to see what that frame actually looks like, both the original and both of the encoded files, you click Show Frame, and then you can toggle through the frames. And we'll see what that looks like in a minute. So here we have, this is just an example. Here's the VBR encoded file, and here's the CBR encoded file. So again, even though the scores are fairly close, you see that there are some regions within the video file that are going to affect overall quality of experience. And then one of the cool features of the Moscow University tool is you can select bad frames. So what bad frames does is it saves the worst quality frames from the different files that you're evaluating. And why do you care about that? Because you only see this if you're using the user interface. If you're producing it from the command line, you don't have the ability to see that graph. But you can produce these bad frames, so you can come back, go to the folder where you save the bad frames, and then see, okay, frame 3820 had a VMAF rating of 40. And then you actually see the frame, obviously not just the upper left-hand corner. So, and we're gonna go through the logic I use when I'm evaluating compression technologies and when I'm evaluating, anything that's compressed. And we'll see that you always have to look at bad frames because, again, if you just look at the overall score, you're going to miss this type of stuff. So if I did this from the command line and I enabled bad frames, it would save this frame, it would save this frame, this frame, this frame, and then I can go back and look at it later. I can run 100 files and get the worst 5 frames from each of those 100 files and go back and look at it later. So what do I like about Moscow University tool? It's $1,000, very, very inexpensive. GUI and command line, it's very visual. We saw that. Multiple algorithms. My review is here. And cons, you can only compare files of like resolution, like frame rate. There are workarounds. You have, if you're looking at the quality of a 360p file as compared to the source file it was encoded from, you have to scale it up in FFmpeg to 1080p. Not a big deal, but if you're doing 100 files, and it's a 2-minute file, all of a sudden you need 2 terabytes of data or some. I mean, it gets cumbersome when you have to do that. There are workarounds to that as well, but it's easier if you can just compare without doing the scaling yourself. And then the SimWave VOD monitor, it's based on the SimPlus algorithm. That is a proprietary algorithm by the inventor of SSIM, the original one. And you know, what I like about the SimPlus algorithm is that it corresponds with predicted subjective ratings. So if you get a score of 45, you know, okay, the typical viewer is going to look at that and say, it looks fair. If you get a score of 80 and above, they're going to look at that and say, excellent. And also, as we covered a few slides ago, excellent ratings for different devices. So if you want to gauge how an encoding ladder will look on 5 different mobile phones, you can do that. And you really can't do that with any other technology. It can compare different resolutions without conversion, so that's very nice. It can compare different frame rates without conversion. Runs on CentOS, Mac, and Windows. My review of the end-of-life Windows product is here. They have a more advanced product now that I have running but haven't reviewed it. And you know, if you want to see that, they're here at the show. Here I'm covering the VOD monitor. They also have the live monitor, which again is more, you know, how do you monitor the quality of a live series of channels? And that's, you know, very advanced technology, very different from what you see with the Moscow University tool, which is really, you know, one source file compared to 1 or 2 encoded files. And same thing with Tektronix Sentry. So this is, they've got real-time monitoring here. They're at the show, and you know, what they're all about is detecting and alerting on critical issues that impact QoE. So you're not going to use this to compare a compressed file to a source file, but you will use this if you want to make sure that all of your channels are running smoothly and you don't have any quality of experience problems. So again, they're here at the show as well, and I recommend talking to them if you're interested in that type of product. Okay, so how do I compare, you know, CBR versus VBR? And you know, why do we care about this? Because we have to make recommendations about how people should encode. And I have a book out. It's called Encoding by the Numbers. And what I tried to do with that book is, you know, everybody has opinions, and everybody argues what's better, CBR versus VBR. And what I tried to do with that book is just quantify everything. So I don't say VBR is bad, you know, CBR is good, or vice versa. I say if you encode with 200% constrained VBR, you get a VMAF rating of 80.47. If you encode 79.97, or I'm sorry, if you encode with 1-pass CBR, you get 79.97. So that's step one. But what does this tell you? You know, we covered the fact that VMAF ratings have a 6-point just noticeable difference. See, we look at this and say, okay, well, there's no just noticeable difference. Again, let me just encode with CBR. I'll save an encoding step and cut my encoding costs in half. Then you look at this results chart and you say, holy cow, there may be some problems. And I'm not quite sure how this is going to work. And I'm probably going to skip it anyway. But this is, you guys have seen the results chart. This is a video file that's embedded in the PowerPoint file. I'm not sure how this is going to go with this device. But here, yeah, let me just skip that. So I would look at the frames. Here's the original frame. Here's a constrained VBR frame, and here's the CBR frame. So what doesn't that tell you? When you look at something like this and you say, this frame is really ugly, what doesn't that tell you that you really care about? Say it again? How noticeable it is? Perfect, very good. So do we care about a 1-frame artifact? You know, we kind of care, but is that enough to go one way or the other over a particular technology? So what I do then, and you know, the point you made, excellent, is can I see the difference in real time? And what I do after I come up with an analysis like that is I load the 2 files into Adobe Premiere Pro. You can use any editor. Premiere is really good because it accepts a whole bunch of different file formats. I set them up on a timeline. I put them side by side. There's a little bit of cropping involved to get them both on the same timeline. And then Premiere lets me use frame counts. So I can go from the frame numbers here to the frame numbers here, and I can just run the video side by side and see, is there a difference? Because really, we don't care about a single frame. We care about what's it going to look like if a typical person views it. And I just compared technologies for a vendor, and we looked at 4 different video files, 7-rung encoding ladder, you know, 2 different technologies. So it was dozens of setups like this. But just because you see a bad frame doesn't mean a viewer is going to see it. So this, the analysis that I like to do before I say this technology is good or this technology is bad, and actually, let's see if we can watch this. So this is the one-pass CBR. This is the constrained VBR. And you can run it multiple times to kind of get a gauge of it, but it gives you the ability to make the critical link to, is there a problem? Is there a problem people will see? So what I do when I'm making encoding decisions is I run tests, I review the plot, I look at the bad frames, I play the video, usually inside of Premiere because I like the structure of being able to repeat it. I like the structure of being able to output that. If I'm telling a client, look, this is visible, I can send them a video file from Premiere and say, look at it yourself. This is not, so it's repeatable, it's objective, and it really gets to the heart of the matter, which is, will people see the difference? So if you're using objective metrics, never make the comparison on the basis of a single number because that really tells you very little about the overall quality of experience. You've got to dig into the individual frames, and then you've got to take the extra step of making sure that the bad frames that you see are going to be visible to the typical viewer watching the video in real time. So who here is using per title encoding? Anybody? OK, so per title encoding is a technology that creates a different encoding ladder for each piece of content or each category of content. And what I'm going to walk through here is how I would do that for either specific bits of content or specific categories of content. And what I do is I use constant rate factor encoding, or CRF. And CRF is encoding mode available in X.264, X.265, and VP8 and VP9. And CRF encodes to a specific quality level, not to a data rate. So you can use it as a gauge of encoding complexity. And if you use it with caps in a technology called cap CRF, you can also use it as a per title encoding technique. And we're not going to cover that. So what you do is you choose a range, and the range that I think corresponds with what I'm going to call Hollywood quality, and you'll see why I say that in a second. If you encode at CRF23, and this is what I did for the book that I just mentioned a few minutes ago. I had 8 different source files. I encoded them all to CRF23, and then I measured the VMAF score. So we see the data rates here range from 1 megabit per second for a simple tutorial, which is PowerPoint and talking head, all the way up to 6.1 megabits per second for a 30 frame per second, kind of a scary movie type video clip, and 5 megabits per second, or 5.168 for Syntel, and then 4.747 for Tears of Steel. And these are both 24 frames per second. So what does this tell you about the encoding complexity of the different clips? Which clip here is the hardest to compress? OK, the one with the highest data rate. And if we look at the VMAF score, we see that the VMAF scores are all relatively similar. They're all, this is 92, this is 95. They're all in this same range, and the standard deviation is 1.39. So what that tells you is that a CRF23 encode will produce a file that gives you a VMAF score of somewhere around 93, which is our target, because that's what we saw from the RISA Rasul real networks. So basically, you've got, if you use CRF23, you can predict, how do I figure out the quality that will be non-objective to my viewers? What's an appropriate data rate for my 1080p highest quality file? And if you use CRF23, you get that. And then Hollywood verification, what I did was download a bunch of video clips from iTunes. And these are 1080p clips, most are 23 frames per second. And the average data rate was 5.1 megabits per second. And the two 24 frame per second files that I looked at in this previous page, Tears of Steel and Syntel, their average data rate was 4.95. So Hollywood's data rate was very similar to my data rate, which is why I think I get verification that Hollywood thinks that the the CRF23 value and the VMAF93 values are all pretty good measures of video quality. Here's the Real Networks paper. And again, I'm going to have this will be up on my website, Streaming Learning Center, within 10 or 15 minutes after this is over. So don't feel like you have to write anything down. And then another reality check for CRF23 was I uploaded all the files to YouTube, and then I downloaded the 1080p file, and then I measured the data rate. And what I see is, what we see is a very similar pattern. Brown is YouTube, CRF23 is this grayish color, and we see that YouTube did the same thing that CRF23 did. YouTube has a very sophisticated machine learning, artificial intelligence-based encoding scheme. CRF23 pretty much did the same things, that it was 1 megabit per second higher. So if you're trying to find an acceptable data rate for your 1080p files that people will be pleased with, CRF23 works. VMAF93 works. And once you have the highest value for each file or each category of files, you choose the highest, you choose the lowest, you fill in the blanks, and then you keep the data rates between 150 and 200% apart. Those are Apple recommendations because you don't want people, if the rungs are too far apart, people get stranded at lower rates. If the rungs are too close, there's too much switching with no real benefit in quality. So the magic number from Apple's perspective is 1.5 to 2x. So for me, if I was doing a group of files for a category or a single file, if the CRF value was 23, I would say, okay, that's my top rate. I would say, how low do I want to go? What mobile devices do I want to serve? And then I would just fill in the blanks using that 1.5 to 2x mathematics. Very simple. Now, how do you choose the resolution for these data rates? And this is a technique that Netflix came up with, very, very innovative, but very compute intensive. Okay, Netflix has a very different problem from YouTube. YouTube is accepting like 300 hours a minute of video. So they need to come up with a number that delivers good quality, but they can't spend hours doing it. Netflix, with Ozark, they might have 16 million people watching a particular video file. So they want to come up with the absolute best quality at the lowest possible data rate they can come up with. So what they do is they encode all the files at multiple resolutions and at multiple data rates. And then they basically choose, our data rate for 4600, well, that's the 4K file in this case. Data rate at 3 megabits per second, that's the 2K file. So basically what I'm showing here is the highest value for each data rate is in green. Does that make sense? So all this is pretty simple once you set it up, but it's very brute force. You encode a lot of files. You make a lot of entries. So for the encoding ladder that we looked at a moment ago, this is what it would come out at. And just for fun, a short pictorial about how this process and it's Netflix's process. I kind of, I wrote about it and I use it in my consulting practice, but it's Netflix's. But in 2017, Apple came out with their recommendation of accepting HEVC in the HLS spec. So the first recommendation they made was to keep the same resolution for the same data rate in HEVC and H.264. Okay, so these are the first recommendations they made. I wrote a story for Streaming Media Magazine. Apple got it wrong, the encoding specs for HEVC and HLS. And basically what I said was you shouldn't use the same resolution for the same data rate if you're using HEVC and H.264 because HEVC is a more efficient codec and it's going to give you better quality at a higher resolution at the same data rate. And then I kind of proved that with this. So this is H.264, same analysis that we saw a moment ago. And for this particular file with H.264 at 1.4 megabit, at 3,600 kilobits per second with H.264, the 720p file was the highest quality. With HEVC at 3.6 megabits per second, it's still 1080p. So you can push higher resolutions down further in the encoding ladder with more advanced codecs, whether it's AV1, HEVC, VP9, VVC, whatever. So you should, so Apple's recommendation, I kind of criticize that. Why is HEVC more efficient? Because it's bigger block sizes, more efficient in a lot of ways. And then Apple came out and they had two separate tables for HEVC and H.264. This is the HEVC, same resolution, same data rate. This is HEVC, which is now 640 by 360 instead of 416 by 234. Long way of patting myself on the back in front of people. But it's really more the fact that you shouldn't use the same encoding ladder for higher quality codecs than you should for H.264. And what they didn't do is they didn't change the switch points. So this was kind of disappointing. They go from, if you look at 34, here it's 3 megabits per second at 720p. Here it's still 720p at 34. And for most of the encoding ladders I looked at, you can push the higher resolution down much further with HEVC than you can with H.264. So Apple made a good step. They didn't go as far as I would like, but the overall point is if you're doing encoding ladders, don't use the same resolutions for H.264 as you would for other more advanced codecs. What about different types of content? Same deal. This is HEVC, Tears of Steel, and this is Syntel. So this is mostly real world and computer generated stuff. This is pure animation. And we see that in the pure animation, we can push the higher resolution videos down further into the encoding ladder than we can with regular video. So if you were producing per title encoding, you're going to want a different starting point in terms of data rate for your different videos. In this case, we might start this one, for Tears of Steel, we might start at 2 megabits per second. And actually, it's pretty close. We would start at 2200 kilobits per second here. But you're also going to have different resolutions at different points in the encoding ladder. Here's the book. Some of the things I studied in the book, how is bitrate control affected by overall VMAF quality? I had animations, synthetic videos, and real-world videos. And here we see 200% constrained VBR, 110% constrained VBR, one-pass CBR. We see quality goes down for all the video files except for the synthetic videos, which was actually pretty interesting. So if you're encoding screen cams, you're encoding PowerPoint files, you may not want to use 200% constrained VBR. But we're not seeing a significant difference. We're seeing the difference between here it's 97.25 down to 96.75. Again, not a just noticeable difference until you start looking at low frame quality, which we kind of beat to death a few minutes ago. And we see, in terms of animations, low frame quality really, really drops with one-pass CBR. So even though it looks pretty good from this perspective, I would not use one-pass CBR particularly for animations. Okay, a few other encoding configurations that I've looked at from an objective quality metric perspective. What are presets? This is choosing the X.264 preset. Presets give you the ability to trade off quality versus encoding time. Virtually all X.264 encoding tools give you the choice of preset here. Medium is the default. Is that a good choice? Again, I looked at the same 8 files, encoded to all the different presets, measured the encoding time, and then the VMAF score. And here's the results. Red is always bad, green is always good. And we see that with X.264, placebo doesn't give you the best quality, very slow gives you the best quality. So that's one of these instances where it's like, well, holy cow, it doesn't make sense to use placebo because not only is it 3 times longer, it's actually slightly lower quality. And then ultra fast and super fast down here, they're the red. Obviously, they're going to give you the lowest quality. Again, we're only seeing a 6% overall difference in terms of our overall VMAF score between, this is 90.53, this is 95.55. So it is about a just noticeable difference. You probably would notice the difference between this one and this one. You probably wouldn't from this one, these here, to this one here. What does this look like if you were plotting it out? Here's the lowest acceptable quality. That's where I would start. I think that's faster. This is the encoding time, and this is the percentage. This is basically the VMAF score. So we saw it was a pretty small difference in terms of overall quality. Encoding times kind of get crazy once you go past the faster. What about the low frame quality? If you use ultrafast, and ultrafast is here. We saw there was just a noticeable difference. It's not only overall quality, it's also low frame quality. Very, very big differences in quality, and some of those are going to be very visible to your customers. This is an interesting problem because if you're encoding live or you're transcoding live, you've got to pick a machine. And then the first thing you do when you pick a machine is you start to run your profiles, and you say, okay, well, can I encode medium? Maybe not. Can I encode very fast? Maybe so. Can I encode ultra fast? Yeah, you can, but there's going to be significant quality issues, so maybe it's time to pick up a more powerful machine. And keyframe interval, same kind of deal. When we first started encoding files before adaptive bitrate technology, everybody used 10 to 20 second keyframe interval. There is a significant quality difference. These are the 6 real-world and animated files. This is the screen cam and tutorial, my synthetic files in the book. We see the difference between 0.5 seconds. The average is 39.26, 40.75 for 10 seconds. Again, not that huge a difference. So this is what we're looking at. So people who fight and say, well, you've got to go higher, 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 or the difference between 2 seconds and 3 seconds if you're encoding for an adaptive group, the overall quality difference just isn't that significant. And then low frame quality, again, always measure that, and you see significantly worse low frame quality with shorter keyframe intervals. So I would not use 1 second. The difference between 2 seconds and 3 seconds is pretty minimal. So either one of these should be fine. I wouldn't go lower than this. And if you're encoding for adaptive bitrate, you typically can't go in these two anyway. And then in terms of how low you can go, how high should the video be in your encoding ladder? This is a chart I put together using SimWave SQM scores. So we've got a bunch of different video clips here. We know with SimWave that if you're between 80 and 100, your video quality should be judged as excellent by your viewer. And here we're seeing, sorry the colors are a bit consistent, but I think Zoolander is the only clip that drops below 80 before 3,500 kilobits per second. So what this is telling us is that if you're encoding your 1080p files at 5 or 6 megabits per second, you probably are wasting bandwidth because you could encode at much lower data rates and still be in the 80 to 100 range that will be viewed as excellent by your viewers. And this, in short, is why it's lovely to talk about advanced codecs like AV1 and even HEVC, but per title encoding is much more important because you can gain a lot of the same benefits of changing codecs by using per title encoding without doubling your encoding costs, without doubling your storage costs. And that's why, if you take one thing away from this conference, one thing away from this talk is that, per title encoding is pretty easy to implement it. It's the fastest and easiest way to get a lot of the benefits that people are saying you should move to a different codecs for with a lot less hassle. And then animation, kind of the same thing. Basically what we talked about before, you get the same quality with animated video at a much lower data rate. So here we're seeing with real world video, we get a 9171 at 8,500 kilobits per second or 6,800 for 24 frames per second. We get the same quality down here at 5,500 or 4,400 kilobits per second. So we're saying basically per title is what you should use. And then if you're going to be running any of these tests, you absolutely need a fast machine with an SSD drive. You can't live with a normal hard drive. because it just takes incredibly longer for even simpler calculations. I've got a HP Z840 workstation that I use, 40 cores, and it's got multiple SSD drives. Sometimes I have to use a fixed drive if the files are too big or if I'm running out of capacity. It just really slows things down. So if you're going to do this stuff and you're going to run it in your own shop, then get a hefty computer, get SSD drives. Any questions?
How would you go about building the ladder for live type applications?
Good question. So how do we go about doing the ladder for live? Typically what I do for live is I get some test footage, and then I just run the same kind of tests. I simulate a live, which is easy enough to do, and then I run the test, figure out the encoding ladder, and do it that way.
Follow up on that. How do you align the frames for the tools to comparison?
So how do you align the frames for the tools? That's a great question, because one of the things about all these tools is you need frame-by-frame alignment, otherwise the tool doesn't work, right? Because you can't compare frame 3 with frame 5, because then the score is going to be awful. Used to be a very significant problem. All the tools give you the ability to adjust frames manually, but really if you do a simulated live capture, you shouldn't have a lot of frames that are out of sync. I've done 2 or 3 of those in the last few months, and it's pretty simple. If you just send it a file, it's the same as you don't want to try and simulate live by sending it a stream, because that's where you run into problems. But if you just feed it a file, it's doing the same thing, and it's going to produce a file that's going to have aligned frames. And the other thing that I would recommend doing is always, 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 if you're going to run some tests, create a file that's got timecode in it, because otherwise it's impossible to align the frames. Any other questions?